Welcome back. So now we're going to start to formalize some of that intuition that we've been developing in the previous lecture for analyzing the efficiency or the runtime efficiency of algorithms. We're going to take that sort of heuristic-like thing we did and start to really sort of tighten it up a little bit and more formally. All right, let's start with the linear search, and let me remind you what the algorithm is. So we have our function linear search. It takes a list, which is not assumed to be sorted or any order, a key, and I want to return the index of where the key is found if it's in the list, and none if it is not found in the list. I initialize an index variable to be 0. I iterate, this is my while loop, as long as the index is less than the length of the list. I check to see if the key is the indexed element of the list, and if it is, I'm done. I found the element, get out, return index, and if it's not, keep incrementing index by 1. And for the analysis from now on, although it is important to always think about best case and worst case, and you'll see eventually on average case, we're going to talk about the worst case because that's just the more interesting analysis. The best case is always trivial. You stop at the first comparison. So we're going to think about the worst case analysis here. And what we're going to do is look through this code and try to figure out what is the cost. Well, what's the cost? Every time you evaluate an expression, it costs you something. It costs some number of cycles on the computer. So for example, when I initialize a variable index to be 0, it costs me some amount of time, which I would denote as C1, C for cost. What is that cost? Well, it depends. It depends on your computer, how fast it is, what else is running on the computer, how much memory you have on the computer. But for now, we can just sort of abstract it out to there's some fixed cost. Now, remember that runtime complexity is always evaluated in terms of the size of the input. Notice that this cost has nothing to do with the size of the input. It's constant. Why? Well, because I'm just evaluating this line. This line of code doesn't cost me any more or less depending on how big that is. And keep that in mind, that there will be some costs associated with an algorithm that depend on the size of the input, and some are fixed costs. You just do it once, and you're done. Now, this while loop obviously depends on the size of the input, which we will denote as n. Why? Well, because that while loop is going to iterate n times. And if we assume the worst case scenario, which is that the key we're looking for is either the last element of the list or it's not in the list at all, we're going to have to run through this while loop n times. And that means we have to do what? We have to do that comparison, and that increment. So let's bundle all of that cost up into C2. So why am I doing this? Well, I know that I'm going to run this loop n times. And I'm simply bundling up C2 to be the cost of that comparison, by the way, and that calculation right there, computing the length, that comparison, and that increment. There's some cost associated with it. But notice in particular that the cost depends on the size of the input. This fixed cost doesn't depend on the size of the input. This, because it's inside of a while loop, is going to cost me depending on how big the input is. It depends the size of the input, the list. All right. Last thing is we have that little cost right there, which is a fixed cost, C3. So that's a one-off. We do it once, and we're done. So what's the cost of this algorithm? It's C1, initialize a variable. C2 times n, the size of the input, the cost associated with running that while loop, plus C3. What's C1, C2, C3? We'll worry about that in a little bit. Let's not worry about it right now. But you get a sense of why this is now a linear in the size of the input, because as I increase the input, that cost goes up proportional to the size of the input. And then there's these small constants here which don't really matter that much, right? Because as that gets bigger and bigger, those constants are going to become more and more, less and less significant. All right. Now, let's think through the binary search algorithm. So how did the binary search algorithm work? Well, there's some return statement at the very end, of course, so that's going to be a fixed cost. And then there was the comparison that had to be done, whether I search for the left side. We compare it to the midpoint, and then we either search for the left or search for the right. That had to be done log n times, which we saw earlier on by looking at that table that said, as the input doubles, what happens to my cost? It was log n. I've dropped the +1 now because it's just another constant that I don't have to worry about. And inside of that looping, there's some cost, which I will call C4. Okay, so now we have these two algorithms. Linear, which is C1n plus C2 plus C3, and binary, which is C4 times log of n, the size of the input, plus a fixed constant C5. So Which one's better, which one's worse? Well, our intuition, of course, is that log n is much, much more efficient than n. Because remember again, every time I double the size of the input, this only costs me one more, whereas when I double the size of the input, I double the number of comparisons. But what about these constants, right? That C1 and C4 are different, okay? So let's just to give you a sense of the difference between logarithmic and linear cost, let's do a little back of the envelope calculation. So as I said earlier, these fixed costs become sort of irrelevant as n gets bigger. Yeah, so as n gets to be 1,000,000, the fact that I have to do 1,000,002 operations is no big deal. So let's go ahead for the purposes of what we're about to do and what we're going to do later on, just drop those fixed constants. They do not depend on the size of the input n. So let's say that linear is some constant times n and binary is some constant times log n. And now let's think about what is the impact of those constants. Like how big of a difference are these two things? All right, so let's imagine that I'm running this computer, linear search, on a computer that is 1,000 times faster than the computer that I'm going to run binary search on. So what do I mean 1,000 times faster? Well, that constant here is going to be 0.00001, and I'm going to put the constant here to be 0.01. So this is 1,000 times slower than this. Okay? So again, the constants are just how long does it take to execute a command. If I have a slower computer, the constants are going to go up. Okay, so I've made this constant much bigger than this constant. So I'm running binary search on a computer that is 1,000 times slower than running linear search. And for an input of size 16,384, which is just 2 to the power 14, basically these algorithms run at equal speed. And that's sort of amazing already, right? So for a relatively large list, even though linear search is running on a computer 1,000 times faster, that logarithmic search is as efficient as this. Now, what is your expectation? Your expectation is as the input goes bigger and bigger and bigger and bigger, this is going to grow faster, much, much faster than this. So what happens when our input goes to 1,000,000? Well, then the linear search on a computer that is 1,000 times faster is going to take 10 seconds, whereas binary search is going to take 0.2 seconds. Think about that for a second. This thing is significantly faster because it's running an algorithm that is significantly more efficient despite the fact that the hardware it's on is pretty lame, 1,000 times slower. So this should give you an appreciation for the power of logarithmic growth. It grows very, very slowly, one extra step for the doubling of the input, as compared to this that grows linearly with the input. So as our inputs start to get bigger and bigger and bigger, we really start to notice the hit here. Obviously, for a really small n, the difference between these two is negligible. So that's another question you always want to ask yourself is, how big do I expect my input to be? If it's relatively small, well then these issues of runtime complexity are not that bad. But as they start to grow, well then you have to start to worry a little bit more. Okay, that was the first step in formalizing the analysis of runtime complexity or efficiency of algorithm. And now we have to do one more step, which is to introduce big O notation, which is to take those little exercises that we just did and add just a little bit of mathematical notation. And we're going to do that in the last lecture in this series. So I'll see you in a little bit.